The next type of probability I'm going to talk about is what's called the either or the or probability. And it's what we know known as non-overlapping events or events that cannot occur at the same time, such as a person being a smoker or a non-smoker. You can't be both. You can't fall into both groups. Either you're a smoker or a non-smoker. A person belonging to the Democratic Party or the Republican Party. You can't belong to both. You're in either group. When that occurs, we also refer to this as what we know as what's called disjoint. These are disjoint events. So you may see these as the word disjoint. If events are disjoint, that means they cannot occur at the same time. Don't get that confused with independence. Independence means if one happens, the other one can still occur. They have no effect on each other. Disjoint means if this one occurs, then the other one cannot occur. So, and if that happens, what we can do is we can multiply, we can add probabilities. So, or statements really mean to add, just like and statements really mean to multiply. So, suppose you roll a single die. What is the probability of rolling either a 2 or a 3? The first question you should always ask yourself is, can these events occur together? Can I roll it? Is there a number on the die that is a 2 and a 3 at the same time? And the answer there is no. It's either a 2 or a 3, but it can't be both. So the probability of rolling a 2 is equal to 1/6. The probability of rolling a 3 is also equal to 1/6. So when we write the word or the probability of A or B, this can also be written as the probability of A, we call it the union, A union B. And when we look at this problem then, the probability of rolling a 2 or a 3 is equal to 1/6 plus 1/6, which is 2/6. So there's a 2/6 chance of rolling, or 1/3, if you want to reduce it, a 1/3 chance of rolling a 2 or a 3. Now, what if events overlap and we're looking at the or statement? Well, if events overlap now, we run into a problem. And I'm going to display this problem with what's called a Venn diagram. So in a Venn diagram, we draw this rectangle, which represents the entire sample space. And we have two events, event A, do that circle again, event A and event B. And they have overlap. So this is being a female, let event A be a female and event B be a smoker. Well, the overlap right here, is a female smoker, which can occur. So here's how this works though. When we do this, we're going to look at all of the females, which are the A event, all of the smokers, which are the B events. And again, this purple event down the middle are all of the female smokers. We have overlap. Because it's an or statement, we can still add the events. And what that looks like is you're going to add probability of A, so everybody in A, then everybody in B. But the problem with that is that you've added this intersection twice. You've added them when you counted them as being females. You've also added them when you counted them as being smokers. So you've added the female smokers twice. So what we do, and remember, this is an and statement in the middle because you have to be a female and a smoker. And because you've added it twice, you need to go back and subtract it off once to get the final probability. This is called the addition rule. And in the addition rule, it says the probability of A or B is the probability of A, all of the females, plus the probability of B, all of the smokers, minus the probability of A and B, minus the female smokers that we added twice. So look at example 5. The following 8 people are in a room: 2 Democratic men, 2 Republican men, 2 Democratic women, and 2 Republican women. If you select one person that ran from this room, what is the probability that you will select either a woman or a Democrat? So the question is really like this. You can either you're interested in the event of being a woman. The probability of being a woman. Well, there are 2 Democratic women, and there are also to Republican women, right? So the probability of being a woman is out of the total events in the room, there are 8 people in the room, 4 out of 8. The probability of being a Democrat, well, there are 2 Democratic men and there are 2 Democratic women. So the probability of being a Democrat is equal to 4 out of 8 as well. But the problem with this is, what have we done? We've counted the Democratic women how many times? So we have Democratic women, which would be the probability of being Democrat and woman, or woman and Democrat. Well, that is 2 out of 8. So when we do this, addition rule says to add the 2 events and then take off their intersection because you've added it twice. So I'm going to add 4A's plus 4A's. I'm going to subtract out this 2A's because I'm taking away the fact that I've added these Democratic women twice. And so when I get this, I get 6A's, or 3/4. And again, I'm doing this because in this process, I've counted the women, the 2 Democratic women twice here, and the 2 Democratic women twice here. So I have to go back and subtract it off once. That's how I get 6A's. The next example says, at a fictional high school, Statistics High, after school activities can be classified into 3 types. So athletes, fine arts, and other. The table gives the number of students participating in each of these types of activities by grade. What is the probability that a student selected as a 9th grader, or, keyword here being the word or, which means to add, a 9th grader or an athlete? So question is, can you be a 9th grader and an athlete at the same time in this sample? Well, let's look at it. Before we begin this problem, notice that these numbers at the top, the grade levels, are shifted over. So we need to go ahead and correct that before we start, or it'll mess us up. So this should be written here. It should be 9th grade. This should be 10th, 11th, and 12th. And these are the totals for those columns. Now, can you be a 9th grader or an athlete at the same time? Well, let's look at the sample and see. Here are all of the 9th graders in the sample. There are 375 9th graders. Here are all of the athletes in the sample, and there are 600 athletes. Are there any people in the sample that are athletes and 9th graders at the same time? Well, if we look at the table, we can clearly see that those people are sitting here. And we realize that when we do this addition here, when we look at the 9th graders first, we have the probability of being a 9th grader is equal to 375 out of 1,600. And then the probability of being an athlete is equal to 600 out of 1,600. And then we can see the purple shaded region. It's the part that got added twice, the 150 people that are athletes and 9th graders. So the probability of being a 9th grader and an athlete is 150 out of 1,600. If we add up these, so again, we're going to do this. We're going to add these 2 events up, the or part of those events, and subtract out their and, because you're adding the and twice. So when you do this, you get 375 out of 1,600 plus 600 out of 1,600. And then you're going to subtract off that intersection, which is 150 out of 1,600. And when you do that, you get 825 out of 1,600. And remember, we're subtracting this off right here. We're subtracting this 150 off because we've added it when we did the red and the blue, or the 9th and the athletes. So we added it twice. We need to subtract it off once. Look at the next one. It says What is the probability that a student selected is an upperclassman? And defining that as a person that is in the 11th or the 12th grade and in fine arts. So I have two conditions I'm placing on this. So first part says 11th or 12th grade. That would be these 410 people in the 11th grade, these 425 people in the 12th grade. Can you belong to both groups though? No, you're either in the 11th or your 12th grade. So those are what we call disjoint events. And you may see that written as what we call mutually exclusive events. Mutually exclusive meaning that it excludes you from one group. You belong to one group and not the other. So if you see the word mutually exclusive, that also means that they are disjoint. And when we do this, then we're going to write this as how many 11th graders are. The probability of being in 11th grade is equal to 410 out of 1600. And the probability of being in 12th grade is equal to 425 out of 1600. And we know those don't overlap, so we don't have to worry about subtracting anything off. The second part says, though, out of these people, how many people is that total? So the probability of being in 11th or 12th, adding those events up is equal to 835 out of 1600. Now, out of these 835 people, the next part says how many of them are also in fine arts. Well, you can see out of that, these people right here are in fine arts. So selecting an 11th or 12th grader would be these people right here. And out of those people, how many are those and how many of them are in fine arts? Well, these 120 plus 125 are those 225 people. Now, do I care now about all of these people sitting inside of here? That's a real question I want to know. Do I care about all 1,600 people? No. I only care about who? The 835 11th or 12th graders. So essentially what I'm doing is I'm restricting the people that I'm interested in. Instead of looking at all 1,600 people now, I'm only interested in 835 people. And out of those 835 people, I'm further only interested in the 120 in 11th grade and the 125 in 12th grade that are in fine arts. So that's a total of 245 people. So the probability of finding somebody that's an 11th or 12th grader and in fine arts is 245 out of the 835 11th or 12th graders. The last thing we're going to talk about when it comes to independent rules and addition rules is what's called the at least one rule. And this is for independent events. And it says this: the probability of finding at least one of something, at least one. And we can go back to the example of tossing 3 coins. And remember we made a table for that. And the table looked like this. If you want to look at least one head, well, here are all the possible probability or the possible outcomes for at least when you throw a head, when you throw 3 coins. There are 0 heads, 1 head, 2 head, and 3 heads. And the probability of each event we've already calculated to be, the probability of 0 heads was 1 out of 8. 1 head was 3 out of 8. 2 heads was 3 out of 8. And 3 heads was 1 out of 8. And remember, this is a valid distribution because these all add up to 1. And here's how we're going to use this to solve it. If we look at this table, which we've created, we know that the probability of at least 1, when I say the probability of at least 1, this term I'm calling at least 1x, at least 1 means it has to be greater than or equal to 1. At least means greater than or equal to. For instance, if I say I'm going to pay you at least $5, it means I'm going to give you $5 or more. In this case, I'm going to give you at least 1 or more. We can see that that's equal to all of these events right here. Here is at least 1. And we can use these tables just to calculate. See that it's 3a's plus 3a's plus 1a, which is 7a's. So the probability of at least 1 is 7a's. But this is for only an event with only 3 outcomes, with only basically 4 outcomes. Here are your 4 outcomes, 0, 1, 2, and 3. What if there were more outcomes? And what if you didn't want to make this table every time? Well, there's a much quicker way to do this, and it's using the complement. If we know that all of these events have to add up to 1, which we do because they're a probability distribution, they have to add up to 1, then look what I've done. I've excluded, I've included every event. I've included every event except the 0 case. So a quick way to do this is to calculate the 0 case. And we can always calculate the 0 case of an independent event by just multiplying the 0 event or the not event, whatever amount of times we're looking at it for. And so here, all I have to do is look at my 0 event, which is 1/8. The probability of getting at least 1 head is equal to, well, I know that these have to add up to 1, so that's 1 minus the probability of the none event, or the no event, or the 0 event. In this case, that 0 event is 1/8. So 1 minus 1/8 is 7/8. Now, with this particular problem, another way to do that would have been the probability of getting a head on any particular throw is 0.5. I'm interested in getting no heads, which means I'm getting all tails. So the probability of getting all tails would be 0.5 times 0.5 times 0.5. Or let's not use 0.5. Let's actually do 1/2. Probability of a tail times 1/2. Probability of a tail again times 1/2. Why am I writing it like this? This means that I got no head on the first toss, no head on the second toss, no head on the third toss, which means these are all tails or no heads. 1/2 times 1/2 times 1/2 is 1/8. So this is the probability that X equals 0 heads right here. What's the probability of getting no heads? 1/8. And again, to find this probability, I would take it, do 1 minus the none case, and that'll give me the at 1 case. So look at the last example, example 8. You purchase 10 lottery tickets for which the probability of winning some type of prize on a single ticket is 1 in 10. So the probability you win is 1 in 10. The probability you lose, which is what I'm actually going to be interested in, the probability of a win is 1 in 10. The probability of a loss is 9 out of 10. What is the probability that you will have at least one winning ticket among the 10 tickets? Well, here's what you need to do. We're going to calculate for 10 tickets. The only thing you're going to be interested in is the probability that you lose on all 10. So that would be 9 out of 10 times 9 out of 10 times 9 out of 10 times 9 out of 10. All the way down to you got, this is the first one, second, third, fourth, all the way down to the last one, which you would have it written as 9 out of 10, 10 times. So essentially what you're calculating, the probability that X, and we're going to let X equal a winning ticket. So X equals 0 means no winning tickets. That's 9 out of 10. How many times do you have it? Raised to the 10th power. This means that you didn't win on any of your tickets. All of these tickets were losses, because the probability of winning again is 1/10. This means that all 10 tickets were losses. If I want to find the probability of having at least one win, then all I have to do is take 1 minus, this is the 0 case right here. Take 1 minus the 0 case, which is 9 out of 10 raised to the 10th. The probability that I win at least on one of these tickets is going to be equal to 0.651. So if I buy 10 lottery tickets, there's a 65% chance that I should win something. And again, this is me using the complement, the 1 minus the none case, basically, to achieve this.